All right, so this is a review for our quiz, which kind of summarizes everything that we've done in this unit so far. So we're just going to go through kind of all of the pieces together. So then hopefully we're ready for our quiz. So the first one says, for each of the tables, identify if it is or not a probability distribution. If not, state which rule it does not follow. So remember, there are two rules to our probability distribution. Rule number one is that if I add up all of my probabilities, it has to equal 1. So the sum of all of them should equal 1. Then my second rule is that all of my probabilities individually need to be between 0 and 1. So that means no negatives, no negative numbers, and no probabilities that are bigger than 1. Right? No numbers greater than 1 in our probability. So we need to just look to see either of those rules. So the second rule is the easiest to check. Are any of these values negative? Yes. This one is negative, so therefore this is not a probability distribution. All right, this one, no negatives, nothing greater than 1. This one, no negatives, nothing greater than 1. Okay, so then we'll check the first condition. If I add up these values, does it equal 1? Yes, so this one satisfied both rules, so we should be good to go. Let's check our other one. This one does not add up to 1. So that cannot be a probability distribution. Okay. So then if we look at number 2, so this is a probability distribution, so all of these would add up to 1 if we put them together. So first we're looking for any unusual results. Remember, it's unusual if the probability is less than or equal to 0.05. So x equals 4 would be considered unusual because its probability is less than 0.05. Everything else is greater than, so we don't have to worry about that. All right, to make a histogram, remember we're going to put our x values here. So our outcomes are going to go here. So 0, 1, 2, 3, 4. And then our probabilities will go here. Remember, you have to consistently count up by the same amount when you count up for your probabilities. You can't have inconsistent numbering. So then at 0, my probability was 0.49, so almost 0.5. Then I have 0.26, just between 2 and 3, 0.1, 0.13, so just a little higher, and then 0.02, so pretty small. So there is our histogram of our probabilities. All right, so then we need to find our mean and our standard deviation. So remember, to find your mean, you're just going to do x times p of x and add up all these values together. So 0 times 0.49 would just give me 0. 1 times 0.26 would give me 0.26. 2 times 0.1 would give me 0.2. 3 times 0.13 would give me 0.39. And 4 times 0.02 would give me 0.08. And then I'm just going to add up all these values, and that's going to tell me my mean. I don't have to do anything else. So if I add up 0.26 plus 0.2 plus 0.39 plus 0.08, I get 0.93. So my mean is 0.93. So my standard deviation is a little bit different. There's a couple more steps to it. It starts by doing x squared times p of x. So we're going to multiply. We're going to square these and multiply. So 0 squared is just 0. 1 squared is 1. 2 squared is 4. 3 squared is 9. 4 squared is 16. So I'm going to multiply. 0 times 0.49 is just 0. 1 times 0.26 is 0.26. 4 times 0.1 is 0.4. 9 times 0.13 would give me 1.17. And 16 times 0.02 would give me 0.32. So now I'm going to take all of those values and add them up. So 0.26 plus 0.4 plus 1.17 plus 0.32, and I get 2.15. That is not my standard deviation. I need that number, but it is not my standard deviation. My standard deviation is the square root of that number minus the mean squared. So the square root of this number minus my mean squared. So I'll take the square root of 2.15 minus 0.93 squared. And that 1.13 is my standard deviation. Okay. So then the last part of our probability distribution that we did was we talked about events taking place or finding expected values. Remember, if it asks you to find expected values, this just means find the mean. So you enter to join a school lottery event. You buy a ticket for $2. First place, you'll win 100. Second place, you win 50. And third place, you win 25. 1,000 tickets were sold. So the possibilities of this event, you could lose altogether. You could get first place, second place, or third place. Right? Those are the only options here. You win first, second, or third, or you lose. Event in numbers just means what was the cost or what's the number outcome here. So if you lose, all you do is lose the $2 you lost from that ticket. If you win first place, you don't necessarily win $100 because you put $2 in. So you win $98, right? You profit $98. You gave them $2. So you're getting $2 back plus an additional $98. Same thing for second place. You wouldn't win 50, you would win 48. And then you wouldn't win 25, you'd win 23. Because you're always taking into account the $2 that you put in. So then if we think the probability of all this happening, there are 1,000 tickets. So only one out of the 1,000 tickets will win first place. Only one out of the 1,000 tickets will win second place. Only one out of the 1,000 tickets will win third place. So then remember, all of these have to add up to 1. So if you've used 3 out of 1,000, that means there's 997 tickets that are not winning anything. All right, so then to find our expected value, we're going to do x times p of x and then add it together. So I'm going to do negative 2 times 997 divided by 1,000. And I get negative 1.994. Then I'll do 98 times 1 over 1,000. And I get 0.098. Then 48 times 1 over 1,000. And then 23 times 1 over 1,000. So now, remember, expected values just mean, so I'm going to add all of these up to find my expected value. And I end up with negative 1.825. So this game is not fair, right? We're expected to lose way more often than when we win. All right, so that was kind of all the stuff that went with our probability distribution. So then we started talking about our binomial distribution. So remember, for your binomial distribution, you need 3 things. You need an n value, which represents the number of trials. You need a p-value, which represents your probability. And then your x value is the outcomes that you're looking for. So it wants me to make a table for n is 3, p is 0.48, and then for each of these x values. So remember to do that on our calculator. We hit second vars, and then we're going to scroll all the way to our normal or binom PDF. For most of you, that should be letter A. And then my trials, my n value is 3. My p-value is 0.48. And then my x value we'll start with is 0. So I get that when it's 0, I have 0.141. So then I'm going to keep the same n and p value. So I'm just going to copy and paste this. And then I'm just going to change x to 1. So now I have 0.389. And then again, I'm going to use almost all the same information. So if you highlight what you want and hit enter, it's going to copy and paste it below and make it so you can edit it. So instead of 1, I'm going to put a 2. And then it tells me that for 2, I have 0.359. And then I'll change this to 3. And I have 0.111. And those would be all my probabilities. All right, we're going to continue with our binomial on the back. So if you turn your paper over, we'll look at some scenarios of our binomial distribution. So during a baseball game, a batter will make contact with the ball 62% of the time that he swings. If a baseball player swung at 20 balls during the game, what is the probability he hits exactly 14? So the number of trials, he swung 20 times total. Our probability is our 0.62, and then we want exactly 14. So we're going to make x equal 14. So I'm going to go over here, second vars, back down to my binom PDF. So my n value, my number of trials was 20. My probability is 0.62, and my x value is 14. So I get that the probability is 1447. All right, so the next one, what is the probability he hits more than 17 of them? So this is going to stay the same. More than 17 would mean higher than 17, so 18, 19, and 20. And I'm going to have to find each of those 3 probabilities and add them together. So, again, if I go to my binom PDF, and then I want 20, and then I'll start with 18. And then I want 19 and 20. So again, I'm just going to copy down 18 and change it to 19. And that's my probability for 19. And then I'll change this to 20. And that's my probability for 20. So I want to add those 3 probabilities together. So I'm going to copy that, hit plus, copy the next one. If I just hit enter, it copies it down. Hit plus. And then find my last one. Oops, too far. Hit enter. And then hit enter again to add all of those together. So I get that my probability of those 3 added together is 0.00596. Okay. So now I'm looking for my mean and my standard deviation. So remember, in our binomial, our mean is just our n value times our p value. So I'm just going to do 20 times 0.62 to find my mean. So 20 times 0.62 tells me my mean is 12.4. So then my standard deviation, we do the square root of n times p times q. Well, we know n and p. Q, remember, is just 1 minus p. It's the probability that it doesn't happen. So if you have a 62% chance of hitting the ball, what's the percentage that you don't hit the ball? So 1 minus 0.62 would give us 0.38. So I would do the square root of 20 times 0.62 times 0.38. And that would tell me my standard deviation is 2.17. All right, so then if I'm looking for unusual values, we're going to take our mean plus or minus 2 standard deviations. So that means we're going to do 12.4 plus 2 times 2.17 and 12.4 minus 2 times 2.17. And we're going to find those 2 values. So 12.4 plus 2 times 2.17. And then 12.4 minus 2 times 2.17. So what I get here is 16.74 and 8.06. So this is my range of usual values. Anything that falls within this range, we would be considered to be usual. It would be unusual to get results outside of those values. So for instance, if I asked what's is the probability of them hitting the ball one time, only one time, unusual, we would say yes, because that's outside of our range of usual values. All right, so then that was our binomial, and then we've just started talking about our normal distribution. So in our normal distribution, one of the things we did was calculate our z-scores. So remember, to find a z-score, you take your x value minus the mean and divide by the standard deviation. So just in these two examples here, I would do 80 minus 85.3 and divide by 4.1. And I get negative 1.29. And then here I would do 95 minus 92 and divide by 6. And I get 0.5. Your z-scores can be positive or negative numbers. It does not matter. Remember, what a z-score does is it places your values on a standard normal curve. So where the mean is 0 and the standard deviation is 1. So it places them on a curve like this. So why we find z-scores is because we can take data from different sets and still compare them to one another by putting them on our standard normal curve. So for instance, if we look at number 7, it says Connor and Dylan are running in separate races and are trying to figure out who did better. Connor ran his race in 42 minutes with a mean of 46 and a standard deviation of 3. So I can find Connor's score by doing his score minus the mean divided by the standard deviation. So 42 minus 46 divided by 3, he has a negative 1.33 score. So his would be right about there. Then we have Dylan. Dylan ran his race in 18 minutes. His mean was 15 and his standard deviation was 4. So if I take 18 minus 15 and divide by 4, I get 0.75. So Dylan's score would be right around here on a standard normal curve. So now when we compare these, we're thinking about a race. A lower time means you ran faster. So the mean time is here. So you would want your score to be lower than the mean in this case. So if you want your score to be lower, right, Connor ran faster or ran better. His score was lower than the mean. Dylan's score was higher than the mean, which means it took him longer than the average person. When we talk about test scores, remember we want the highest, the score farthest this way. It kind of all just depends on the context of the problem of how you're comparing them to one another. All right, and then the last part we did was our empirical rule. So remember, if we have the test scores, the average was 21 and the standard deviation was 5. So this would be 26, 31, 36, and 16, 11, and 6. And we can figure out certain percentages or certain areas under the curve just based off of our empirical rule. So the first one says the score is between 11 and 31. So these are both 2 standard deviations from the mean. So remember, when we're 2 standard deviations from the mean, that's 95%. So then the next one says between 6 and 26. So this one, we're not even in how many standard deviations we went away. So over here, we're between 6 and 26. So we want this whole area through here. So when we're uneven, I typically look at each side separately. So on this side of the graph, I'm 1, 2, 3 standard deviations from the mean. So my empirical rule for 3 standard deviations is 99.7 for all of it, but I'm only looking at half the graph. So we're going to do 99.7 divided by 2. And then on this half of the graph, I'm only 1 standard deviation away. So my one standard deviation rule is 68%, but again, I'm only looking at half of that. So I would do 68 divided by 2. So then if I take my 99.7 and divide by 2 and add that to my 68 divided by 2, I get the entire area of both of these shaded regions. So I end up with 83.85. So then the next one asks, what percent of students scored more than 16? So if we're looking at our graph, we want people who did more than 16. So here's 16, and I want everybody over here, including the people that are past 3 standard deviations. So all the way over here. So remember, when I cut my graph in half, this piece is made up by 50% anytime you're cutting your graph in half. So this part is 50% because that's half of the picture. So then I just need to know this part of my graph, which is 1 standard deviation away. So that's my empirical rule. It says 68, but I'm only looking at half of that picture. So I would do 68 divided by 2 and then add the 50% to it. So 68 divided by 2 would give me 34. So then 34 plus 50 would give me 84%. And then it says 68% of students scored between what scores? 68% is our empirical rule for 1 standard deviation from the mean. So that would be between 16 and 26. So that's a review of everything that we've seen so far and what we will see on our quiz.